So my talk will be based around these new types of architectures of AI models and basically architectures of neural networks for combining physics with machine learning and deep learning. So that's why this is the whole presentation is called PhysicsML or SciML. That means scientific machine learning. And I will be talking about how we can harness this new power of AI for technology development. I will be talking about technology development, product development, but also other things, how we can use AI in the healthcare industry, and then extrapolate to how to pick the right technology for using that technology in the healthcare. So first of all, just some information about me. My name is Michal Takáč, and I'm a co-founder and CEO of DimensionLab. We are a company here in Košice, based in Košice. We develop a software platform that uses that basically provides an interface for creating, using, training, and deploying AI-based simulators. So first of all, we need to think about the world around us. It's not static. It's not something that doesn't move, and it's not something that we can model or reduce the complexity of it in such that it's static. We still need to kind of get to a level that we rely on dynamic system, or think about in terms of dynamic systems. Stuff around us, everything that is happening around us can be somehow described by mathematically. So coming back to the notion of black box, yeah, we all kind of are not trusting that much if it's something that we don't understand because it's a black box. But since scientific machine learning is still very, very new, we just have to take more time and study it more. On the other hand, we don't have to rely only on data-driven methods if we have the history of developing these awesome numerical algorithms. As we were mentioning before, that there's a different approaches to working with machine learning methods, or like how to leverage machine learning methods. One is using data-driven approaches, so supervised approach. And in scientific machine learning context, that means that we can extract some simulation outputs, or have multiple iterations from simulations and use that to train it's called surrogate models, or something that you can remove the older model and have this only AI-based model. I want to show you some key components of this revolution that is currently ongoing. And as I've said, the first kind of step in this direction was introduction of physics-informed neural networks. Looking into some practical things right now. As I mentioned, NVIDIA Modulus. Here is an example how you can leverage AI-based modeling for creating a kind of like simulation model or simulator model that can have multiple things inside it that can be used for one, optimizing the design itself, but then doing analysis on the geometry itself, and doing it in a parameterized way. Now, just extrapolating to real-world experience, it's the same code, nearly the same code. The geometry is different, but this was used by NVIDIA to optimize their heatsink. And they used to do these types of simulations for months. It took them literally hundreds and even thousands of hours of simulations in commercial software. And what they did is that instead of kind of manually going through different variations of the shape of the heatsink, they parameterized the geometry and trained it once with all of the information put into it. So all of the equations were parameterized, all of the constraints were parameterized, and you basically then could do something like change the shape of the geometry itself in different ways, and you can run the simulation interactively. Now we get to this was a glimpse into, like the previous slide was maybe some glimpse into where we are going, and that's kind of this notion of combining these new types of AI-driven simulation models with digital twins, and also this notion of creating multiple digital twins with multiple AI, multi-physics models, and connecting them together to create this sort of like industrial metaverse. This is some example of digital twin created in NVIDIA Omniverse combined with NVIDIA Modulus framework to pre-train a model for a heat dissipation and heat transfer throughout the data center. This is how the Omniverse looks like, and I wanted to show you the interface. If you wanted to use it and explore it, you would first have to download the NVIDIA Modulus. So this is static, but if I had a video from this is actually very nice when you put the visual of how the heat is flowing through this, and you can change the slices and you can see everything recomputed in near real time. This is a digital twin created by Siemens Energy, and this is a again a digital twin that combine pre-trained AI-driven simulations with Modulus of water flow through the pipes of some factory, and they are trying to kind of see how the corrosion will kind of be created or something, and they want to prevent that. So this is kind of like predictive maintenance of the pipes to prevent the corrosion. So now I'm jumping into different industry, but stay with me, please, because I want to showcase a pretty interesting use case from healthcare industry. So here in this case, if we are trying to prepare a diagnosis or create a better diagnosis for a patient with aneurysm in their brain, it's super hard to do that for different patients with different geometry of their arteries, of their basically blood vessels and everything. And what you can do is to go through an MRI scan or CT scan and get the geometries out, but you have just the geometries. Now you need to create a CFD simulation of the blood flow in your brain, basically, and that's super complex. Now jumping into other industry, what you can do with these types of AI-driven simulations is to optimize wind farms, but in different way than it was done previously. So now we are able to pre-train the simulation through of the wind flowing through the whole wind farm instead of just one wind turbine, and also check some turbulences, check how one turbine affects another ones, check how different weather prediction will change the energy generation. And then once the model is created, we can combine the weather outputs with the model and generate the optimal solution for me for this country part where we want to put it. And this specific optimization took Siemens Gamesa, this is the company which developed that, 7 minutes. So this takes 7 minutes to do. The weather prediction modeling, this is a very interesting case because like the weather modeling is a super complex problem. Now imagine if you can train the model on the historical data and get the same accuracy for generating the week-long weather prediction in 13 seconds. It's possible, and on your laptop. So you can get not just down on the computational speed, but also on the energy usage of doing that simulation. And I wanted to showcase also something from DimensionLab. And we were approached by a company which developed a model for river flowing into a small hydroplant. And now the problem was that they spent large amounts of time on the extremely complex problem. What we did was that we created few of these AI models. First, it was some custom coding, but then we started implementing some features, some kind of like information about what we learned from creating such model into the product that we developed. And here you can see actually an output from the simulation that is nearly as accurate as the one from commercial software. We actually created 6 types of these simulations or simulator. We created 6 simulators with different architectures in 3 weeks instead of spending 4 years on these problems. So Siml.ai itself is split into 2 parts. The first part that you also seen before in the previous slide, this is mainly about the visual editor. So we provide a building blocks for you to very simply create these types of AI models or AI simulators without coding. So it's a no-code tool basically. You only think about the problem at hand, the physical constraints, the physics model that you want to use, what equation you want to use, and etc. Another part is a simulation studio. So we thought about like why to let people to install different types of software, which is really hard to do. We created a simulation studio which does exactly that. So once you train the simulator, you can preload it and use all of the features that is inside that. So if it's parameterized, it will showcase a UI already for you. The ending thoughts, this technology is still just scratching the surface, but I think it has a great potential.